Hello, this video is for Algebra Textbook, Chapter 1, Lesson 5. That lesson is titled Roots and Real Numbers. The objectives for this lesson are to simplify expressions containing roots and to classify numbers within the real number system. The vocabulary words for this lesson are square root, principal square root, perfect square, cube root, natural numbers, whole numbers, integers, rational numbers, terminating decimal, repeating decimal, and finally irrational numbers. So why learn this? Well, square roots can be used to find the side length of a square garden when you know its area. We'll take a look at that in example 3. A number that is multiplied by itself to form a product is a square root of that product. The radical symbol, shown here, is used to represent square roots. For non-negative numbers, the operations of squaring and finding a square root are inverse operations. In other words, for any number x, as long as x is greater than and not equal to 0, or greater than or equal to 0, then square root of x times the square root of x is equal to x. Positive real numbers have two square roots. The principal square root of a number is the positive square root, and it is represented by this symbol here that we call a radical symbol. A negative square root is represented by the radical symbol with a negative sign in front of it. This symbol here, the radical symbol with the plus minus sign in front of it, is used to represent both square roots. Here we see that 4 times 4 is equal to 4 squared, and 4 squared equals 16. Therefore, the square root of 16 is equal to 4. This is an example of what they're talking about up here, where it says that finding the operations of squaring and finding square roots are inverse operations. They're like the opposite of one another. Here, if we're squaring 4, we would get 16. But if we're looking for the square root of 16, then we would get 4. They're inverse operations. Now let's consider the negative square roots of a number. So here we see that negative 4 times negative 4 is equal to negative 4 squared. Well, since a negative times a negative equals a positive, and 4 times 4 equals 16, therefore negative 4 squared equals 16. So we could say that the opposite of root 16 is negative 4. Another way to look at this is, you might ask, what's the square root of 16? And someone would say, well, it's 4, because they know that 4 times 4 equals 4. They often overlook the fact that negative times negative is positive, so negative 4 times negative 4 would also equal positive 16. For this reason, we can see that, this is an example that shows us that the square root of a positive number can have two answers: the positive form of that number and the negative form of that number. Let's look at our next slide. Now we're going to talk about perfect squares. A perfect square is a number whose positive square root is a whole number. Some examples of perfect squares are shown in the table. So we take the square root of a number, and we find that the square root of that number is a whole number. Then that value that we were taking the square root of is considered to be a perfect square. In the top row, we have a list of the first 10 perfect squares. Actually, I guess 11. It's 1 all the way through 10 plus the 0, so the first 11 perfect squares. 0, 1, 4, 9, 16, 25, 36, 49, 64, 81, and 100 are the first 11 perfect squares. These are perfect squares because their square roots are whole numbers. That is to say, they are non-decimal numbers and they are positive. For example, the square root of 0, well, that's 0. And the square root of 4 is 2. Square root of 25 is 5. You'll note that all of these, such as 64 with the square root of 8, their square roots are indeed non-decimal numbers that are positive, so therefore they are whole numbers, and for that reason they are called perfect squares. A number that is raised to the third power to form a product is called a cube root of that product. This symbol here, the radical symbol with the 3 here, this 3 is what is in the position of what we refer to as the index. So the symbol third or cube root indicates a cube root. Since 2 to the third is equal to 8, the cubed root of 8 is equal to 2. Likewise, the symbol with a 4 in the place of the index and the radical symbol, we would call this the fourth root of whatever number is under the radical symbol. For example, 2 to the fourth power is equal to 16. So, the fourth root of 16 is equal to 2. So let's find some roots. Find each root. Now first, let's look over here at the writing math. The small number to the left of the root is the index. This is what we were talking about before, like the 3 here in example C. The 3 is in the place of what we would call the index. This is where the index of a root is located. In a square root, the index is understood to be 2. For instance, if you look at examples A and examples B, you see that there indeed is not a 2 in the place of the index. In other words, square root symbol is the same as the second root. So what they're saying here is that despite the fact that there is not a 2 in the place of the index, we understand that we are looking for the second root, or that is to say the square root of that number. So here in example A, we have square root 49. So let's look for square root 49. And I am very used to just saying, if we're talking about the square root, of just saying root 49. So from here on out, I'll just, whenever I say root 49 or root of this number, root of that number, I'm speaking of the square root of that number. So root 49, well think, what number squared equals 49? Well, that number is 7 squared is equal to 49. So we've just rewritten root 49 as root 7 squared. And anytime that we have something being squared underneath a radical symbol or a square root sign, then we're just going to get the base of that number, and that's equal to 7. So the square root of 49 is equal to 7. Therefore, it is indeed a perfect square. And the next one, the opposite of root 36. Well, here we have opposite of root 36. What number times itself equals 36? That number is 6. So 6 squared equals 36. So therefore, the root of 36 is indeed 6, or that is to say, any time that we have a number being raised to the second power under a radical symbol, the result is that we just get the root of the power that is underneath the radical symbol. We still have the negative sign. Let's go ahead and keep that. For example C, what is the cubed root of negative 125? Well, this is interesting because underneath the radical symbol is a negative number. We won't be seeing that with square roots because you can't have two numbers that are multiplied times each other and get a negative number. Unless, of course, you use imaginary numbers, and we're not going to get into that here in this lesson. However, if you're talking about cubed roots, you can have a negative number underneath the radical symbol. So we're looking for the cubed root of negative 125. So think, what number cubed equals negative 125? Well, that number would be negative 5. Negative 5 cubed equals negative 125. So this means that the cubed root of negative 125 is going to be negative 5, because negative 5 times negative 5 times negative 5 equals 25 times negative 5, which is equal to negative 125. Wow. Whew. So find each root. Square root of 4 would be 2. 2 times 2 is 4. The opposite of root 25. The opposite of root 25, well, 5 times 5 is 25, so the answer would be 5. So this becomes negative 5. And then finally, the fourth root of 81. So what number times itself 4 times equals 81? Well, I do know that 9 times 9 is 81, but that's only two numbers. However, 9 is also a perfect square, so I know that 3 times 3 equals 9. And then multiply times the 3 times 3 over here to get this other 9 here. So this splits into 3 times 3, this splits into 3 times 3. 9 times 9 equals 81. Therefore, 3 times 3 times 3 times 3 equals 81. Therefore, our answer is 3, because 3 times itself 4 times which matches the value in the index, equals 81, which is our number that is underneath the radical symbol, which the number underneath the radical symbol, even though it's not in this lesson, it's called the radicand. Finding roots of fractions. So here they have find square root of 1/4. So in order to do this, we're going to consider what number can I multiply times itself to get 1/4. Well, that number would be 1/2. 1/2 squared, right? 1/2 squared is 1/2 times 1/2. Multiply numerators, multiply denominators, and we see that 1/2 times 1/2 is equal to 1/4. So therefore the answer is 1/2. There's another way of doing this that I believe is a little bit easier than that. Remember back in the lesson when we were talking about exponents, and we had like 2 to the 2/3 to the 4th power, that is equal to 2 to the 4th power over 3 to the 4th power. Well, it works somewhat similar to what we have here. So here we have a square root symbol, and we have 1/4 is the radicand, the value below the radical symbol. Well, here, let's apply the radical symbol to the numerator, square root 1, over the denominator, square root of 4. What's the square root of 1? 1. What's the square root of 4? 2. Notice we come up with that same 1/2 that they came up with over here. So, personally, it's my preference to do it this way. So let's look at the example here. Root 4 over 9. So root 4 over 9. Let's change that to root 4 over root 9. What's the square root of 4? 2. What's the square root of 9? 3. So this would be 2/3. How about cubed root of 8? 1/8. So we have cubed root, put the 3 in the index, 1 over 8. Let's apply that. Cubed root of 1 over the cubed root of 8. Well, 1 times 1 times 1 is 1, right? So the cubed root, oh, put our cubes in there. Don't forget those. So cubed root of 1 is 1. And 2 times 2 times 2 equals 8. So the cubed root of 8 is 2. Therefore, we would get 1/2. On the next one, we have the opposite of square root 4 over 49. So let's forget about the negative for a while. Just put the negative over to the side, right? And then let's take root 4 over 49, and let's change that to root 4 over root 49. Now let's go ahead and simplify this. Square root of 4 is 2. Square root of 49 is 7. Therefore, the answer would be 2 over 7. All right. Let me erase this here, get that out the way so we can read our next paragraph here. Square roots of numbers that are not perfect squares, such as 15. 15 is not a perfect square. Their square roots are not whole numbers. A calculator can approximate the square root of 15 as 3.8729833346. I think I put an extra 3 in there. Without a calculator, you can use square roots of perfect squares to help estimate the square roots of other numbers. So let's take a look at an example of that. In example 3, gardening application. Nancy wants to plant a square garden of wildflowers. She has enough wildflower seeds to cover 19 feet square, or 19 square feet. Estimate to the nearest tenth the side length of a square with an area of 19 feet square. Well, since the area of the square is 19 feet square, then each side of the square is going to be the square root of 19 feet. Well, 19 is not a perfect square. So find the two consecutive perfect squares that 19 is between. Well, 16 and 25 are perfect squares. 19 would fall right in between 16 and 25. As a matter of fact, if we put a number line here, and we go ahead and put on the number line here, and we put 16 and 25, we see that indeed the number 19 goes somewhere between here. So the textbook's going to show you one way to do this, and as usual, I'll show you another way to do this. So 19 falls somewhere between 16 and 25. But what is a gap from 16 to 25? What is that, a gap of 9, right? So right in between, what number would be here? Well, 8's to one side and 8 to the other. So this would be, what, 8.5? No, I'm sorry, take that back. If we would have a gap of 9, so between there would be a distance of 9. So half of 9, 1/2 of 9 equals 4.5. So right smack in the middle here, 4.5 would be like what, 20.5? And so what, right about here is 20. And right about here is maybe 21. And then what's the distance of 16 to 20? Well, that's a distance of 4, right? So if we split that, 4, half of that, half that, half that, 16, 17, 18, 19, 20, 21. And then if we half and half and half again, 21, 22, 23, 24, and here's 25. So what's the square root of 16? 4. What's the square root of 25? Would be 5. What's right in between 4 and 5? 4.5, right? And right in between those, right about here, would be 4.25. And right about in between those here, somewhere right around here, would be 4.75. Where's 19 at on here? 19's right about here, right? So we would be looking at about 4.25, roughly about 4.35 or so, right? That would be my guess from this. So that's the way I would do it. And then they want you to, let me see, what's the word? Then estimate to the nearest tenth. So I'd be like, oh, okay, well, to the nearest tenth then, yeah, the 3 would get rounded to a 4, so that would be like 4.4. That would be my answer based off of this approach here. So what they've done is they're kind of doing more of a guess and check style type thing. So they're going to take 4.3 and just guess, right? So they're just guessing. Let's take 4.3. Square 4.3, get 18.49. Up, too low. So they're going to go up 1/10 to 4.4. Square 4.4, get 19.36. Oops, too high. So let's go down a little bit. Right in between 3.3 or 4.3 and 4.4 would be 4.35. So we're picking a number right in between these two. One was too high, the other was too low. So go ahead and pick that. And 4.35 squared is this number here, which is still too low, so we'd have to go back up a little bit. So we know that it is somewhere between 4.35 and 4.4. And then they say to round to the nearest tenth. Well, no matter what you do, 4.35 would be rounded to 4.4, and 4.4 would still be 4.4, right? So you know it's somewhere in that area there. So you would round to that 4.4, which is exactly what they've done here. And you can read that if you like, but that's pretty much what they're saying here. Now, also note in the writing math section here, this symbol here that looks like an equal sign with wavy lines instead of straight lines. This means is approximate to. It's like, it's kind of like that kind of like think of it's like almost that. It's approximately that. So think of it, instead of equal sign being a solid straight line saying this is equal to this, it's definitely equal to that. We can say, well, it's about that. It's approximately that. So the little wavy sign is kind of like saying, it's approximately that. All right, let's talk about classification of numbers. Real numbers can be classified according to their characteristics. And down here, I've included a graphic organizer for this. So as I read through the definitions, we'll talk about how do they fall into this graphic organizer here. So first, natural numbers. These are the counting numbers. 1, 2, 3, 4, 5, 6, etc. These little 3 dots here, it's called an ellipsis or something like that. Ellipsis. But it means it keeps going. All right. So those numbers would keep going to infinity. And that's right here at the center of the circle. And since natural numbers are right here at the center of the circle, and that means that natural numbers are not only natural numbers, but they're also whole numbers integers, rational numbers, and real numbers. However, they are not irrational numbers. And how do we remember the name for these are the natural numbers? Well, as a small child, what are the numbers you learn first? Naturally, how many fingers and toes you have. You learn to count on your hands. So remember that the natural numbers are the numbers that you learn first, naturally. Whole numbers are the set of all natural numbers with one element added. That is the number 0. So once we add 0 in, then we have whole numbers. So 0 is a whole number, an integer, a rational number, and a real number. However, 0 is not inside the circle of natural numbers, so 0 is not a natural number. Next we get integers. Integers are the whole numbers and their opposites, such as -3, -2, -1, 0, etc., right? Along with the 1, 2, 3, 4. So here we have integers where they come in. These are the opposite. These are the natural numbers opposites. Actually, they're the whole numbers opposites, such as -1, -3, -2. So integers have stuff on the inside. Notice that natural numbers and whole numbers belong to the set of integers. However, some elements of integers, such as these negative numbers here, are not elements of whole numbers or natural numbers. So integers can be integers, rational numbers, or real numbers. Next we come to rational numbers. Rational numbers are numbers that can be expressed in the form of a over b, where a and b are both integers and b is not equal to 0. You can't have a denominator of 0. When expressed as a decimal, a rational number is either terminating decimal or a repeating decimal. So now we have to understand the difference between terminating decimals, repeating decimals, and also non-terminating or non-repeating decimals. So a terminal decimal has a finite number of digits after the decimal point. For example, 1.25, no numbers after the 5. 2.75, no numbers after the 5. 4.0, it just ends at, it doesn't like keep going and going. It has a point where it stops. It comes to an end. However, a repeating decimal has a block of 1 or more digits after the decimal point that repeat continuously, where all digits are not zeros. Normally you see this, here it is in the writing math portion. To show that 1 or more digits repeat continuously, write a bar over those digits. For example, 1.33333333 keeps going. We could write as 1.3 with a bar over the 3. That's the part that repeats. Another example is a number like 2.1414141414 could be written as 2.14 with a bar over it. The bar over it lets us know which numbers have a repeating pattern. Also, please note the symbols that are used for each of these number sets. Natural numbers is represented with an N. That makes sense because natural starts with N. Whole numbers are represented with this W because whole starts with W. Now here's an interesting one. Integers does not start with a Z. However, I'm sure it has something to do with Greek, right? Rational numbers doesn't start with an R. As a matter of fact, real numbers is represented with the letter R. However, rational numbers are numbers that we can set up as fractions. Fractions are division problems. Division problems involve a quotient. Quotient starts with the letter Q, so you can remember that rational numbers are represented with the letter Q. And there is a one for irrational numbers, and I can't remember it for the life of me right now. I'd have to Google it. I think it might be G or something like that, but I'm not positive. But there is a letter that represents rational numbers. Irrational numbers. Does the next slide tell us what irrational numbers are? Indeed they do. Great. So irrational numbers are all real numbers that are not rational. They cannot be expressed in the form of A or B, where A and B are both integers and B is not equal to 0. They're neither terminating nor they're repeating. For example, look at this one example here. After the decimal point, this number contains a 1 followed by 1 0, then 1 followed by 2 zeros, then 1 followed by 3 zeros, and so on. So this decimal neither terminates nor repeats, so it is an irrational number. It would just keep going and going and going. And a good clue that the number keeps going, and this is very important, is that many times these 3 dots here, ellipses I believe, ellipses, are represent that that number would keep going. There's just not enough room on the page or room on the calculator to show that, right? This decimal neither terminates nor repeats, so it is irrational. One way to remember the word irrational, you ever know anybody that just like keeps talking and talking and talking and they're like crazy and nuts and they just keep talking and talking? People say, wow, they're really acting irrational. So think of it that way. Someone just never shuts up, keeps talking and talking, which you might think sounds like me. Because I talk fast trying to fit all this into the video, one that now I'm at 25 minutes on. But at any rate, there's not a way to remember irrational. Irrational numbers are decimal numbers that do not terminate and they do not repeat. No pattern. If a whole number is not a perfect square, then its square root is irrational. For example, 2 is not a perfect square and the square root of 2 is irrational. The real numbers are made up of all rational and irrational numbers. So any of these numbers that fall into any of these categories are going to be real numbers. The only numbers that aren't going to be real numbers are imaginary numbers. So here we are, classifying real numbers. Write all classifications that apply to each number. 8/9, well, that is a fraction. If we actually did 8 divided by 9, you see that we get a repeating decimal, right? So it would be a rational number and it would be a real number. It does repeat. 18, well, 18 is a natural number, right? Now it can also be written as a fraction, right? 18/1 can be written as a terminating decimal as well. So we can see how it would also be a rational number. But since 18 would fall down here in natural numbers, it belongs not only to natural numbers, but everything as you work your way out of the circle. So 18 is a natural, whole, integer, rational, and real. Square root of 20. 20 is not a perfect square, so the square root of 20 is going to be an irrational number, and it would belong over here with the irrational numbers. All right. And for the rest of it here, let me see, due to time, I think I'm going to skip over a lot of this, maybe do a couple. Vocabulary, give an example of a square root that's not a rational number. Well, we know that if you take the square root of a non-perfect square, or perfect square. So pick a number that's not a perfect square. Well, let me see, 25 is a perfect square, 27 is not, so let's take 27. That would be an example of a square root that would be irrational. Okay, so if it's not rational, then it's irrational. Find each square root. What is 64? What number times itself equals 64? That number is 8. Cubed root of negative 27, so we know it's going to be negative because it's on the outside here. And 3 would be it, right? 3 times 3 is 9, times 3 is 27, so third root of the opposite. The opposite cubed root of 27 is going to be negative 3. And then over here for negative 64, we know this number is going to be negative, and I believe it is 4. 4 times 4 is 16. 16 times 4 is 64, so that number is negative 4. All right. On the next one, looking for simplify each of these. So let's think of this as root 1 over root 16. And if we simplify that, square root of 1 is 1. Square root of 16 is 4. 1/4. And from there, we'll go on with, let's look at down here at number 4. Write all classifications that apply. So negative 27. Negative 27 is an integer. So represented with the little z, right? It's an integer. It's also going to be a rational number, negative 27 over 1, and it's also a real number. So it belonged to all those groups. In this case, 1 over 6 is a fraction, which means we could divide 1 by 6. If we did that, we would get 0.16666, and it just gives you repeating sixes, right? So since it is repeating, this would be a member of rational numbers. So represent that with a Q for rational numbers. And square root of 33. Square root of 33, is 33 a perfect square? Well, 25 is a perfect square. That's 5 times 5. And 36 is a perfect square. That's 6 times 6. 33 falls right in between those. 33 is not a perfect square, so therefore we know that this is an irrational number. And then negative 6.8, it is a decimal number. It does terminate, right? It just stops, so we recognize that is a rational number. It is a terminating decimal. All right, so that completes my presentation of Algebra 1, Chapter 1, Lesson 5, Roots and Real Numbers. Thank you.